morning because I'm not 100% yet. That's good for you.
I mean, do you remember the vibes we had in the evening with labs?
Oh, yes.
It could be worse.
Quite well.
Do you remember what it was like when I was outside?
I'm just saying, all I'm saying, it's all I'm saying. Okay, this week it has been, the weather has been very comfortable, very breezy. Like, what happened to us? We were boiling at this time last year.
That was awesome. That was the worst. Actually, that was kind of the best time of my life.
But I'm really appreciating it because my AC unit went out.
Yeah.
Just come over.
All right, let's get started. We are in lecture 3. Attendance grades are up to date on Blackboard. How was homework 1?
It was wonderful.
Not too bad, right? Pretty straightforward, pretty simple. So you're going to get another homework today, due Monday. It is going to be our first, I don't want to say what we were doing in the last lecture wasn't structural analysis, but we're actually going to be solving some support reactions today and beginning our foray into actually applying principles of structural analysis to solve problems. So I'm going to give you homework 2.1 today that's going to be due Monday. Today what we're going to do is begin our what I would call our first real topic of the class, which is external support reactions. The way that I teach this topic, and really like any topic in this class, is we start out with problems that are inherently basic and very straightforward, and then we just ratchet it up just a little bit from topic to topic. So by the end, we'll be dealing with hinges and concentrated moments and cutting sections and all sorts of out there systems, but we start easy and we just work our way up. So today, all we're going to be dealing with are simple supports, things that are structures that involve hinge and roller type support conditions. And all we're going to be dealing with today are concentrated loads and distributed loads. That's it, okay? And then what we'll do is we'll just take that and extend it, a little bit more complexity. Okay, before I move on, did everybody get the code? See a few people walked in. Everybody get the code? I'm seeing a few people scan. Make sure and try and get the code when you come in. Everybody good? All right. Okay. Okay, so if I can get the slideshow to play, this will be fun. Okay, so let's just sort of recall where we left off last time. We had just discussed classification of structures, and that was really sort of the main focus of both lecture 2 as well as that last homework. But in that lecture, we also defined our 3 most common support conditions for civil engineering structures, and that is the pin or hinge boundary condition, the roller support, and then the fixed support. Okay. In order to solve for these reactions, we're going to use equations of equilibrium. But we're only going to use equations of equilibrium starting out. So what that means is that for the first part of the semester, and really the predominant part of the semester, I would say for at least the first 2/3 of the semester, we are going to be analyzing structures that are statically determinate. Okay? In other words, structures that have an I value of 0. Okay? And the reason for that is that in order to analyze an indeterminate structure, you must first be able to analyze one that is determinate. Okay? In fact, the methods for indeterminate analysis rely on your ability to do determinate analysis. You can't do a determinate analysis, an indeterminate structure is pretty much going to be impossible. So a lot of what we focus on in this class are determinate methods for that very reason. So we're only going to need equations of equilibrium in order to be able to solve these problems. Okay? And so I'm just going to get right into it with our first example, which is this right here. Let me pull it up here on the notebook. Okay. So here's the structure that we're going to analyze. Let's see. So I have a beam here. It's simply supported. So I have a pin and roller boundary condition at A and B. The beam is 30 foot long, and I have 3 concentrated forces on the beam. We have a 20 kip load, a 30 kip load, and an 18 kip load. Now, part of the reason for this, so this problem is really meant to do a few different things for us in here. First, I'm pretty sure you all have done problems like this before. Am I right? You all have done this before. So a little bit of this is tended to shake off the rust, to sort of go, okay, it's been a while. Let's sort of get back into the swing of things. And another way is I want to sort of show you how I approach things and sort of my method for doing this, because we're probably going to do it maybe a little bit differently than you did in Engineering 213 or 216. But there are a couple of caveats to that, like we're not going to use IJK or anything like that in this course. Okay, so let's get right to it. Okay, so we're going to solve for the reactions on this problem, and we're going to do that using our equations of equilibrium. And here are our three equations of equilibrium. Sum of forces in the x direction, sum of forces in the y direction, and sum of moments. So we have three known cards that we can play at the table, as it were. Those are our three cards we can play. And that should be matched against three unknowns if the structure is determinate. By the way, is this structure a determinate structure? Is it statically determinate? How many unknown support reactions do we have here? Two. How many do we have here? So I is R minus E sub C plus 3. There's no internal hinges, so R is 3 minus 3, which is 0. So far, so good? All right. So let's start looking at analyzing the structure. And so what we're going to try and do is determine these support reactions. Now, I'm going to work backwards. I'm going to start off here at the roller at B. We agree that there is one unknown support reaction, okay? And so we're going to start developing a method, and I want to try and be a bit global and universal in how we apply this method, okay? So B has a one reaction, and that reaction is vertical in nature because of the way the roller is oriented, right? This reaction could either act upwards or downwards. Now, without doing any math, how would you all guess that the reaction at B acts, up or down? Up, okay? Now, technically what we're doing right now is we're going to make a guess. We're going to assume that it acts upwards. So I'm going to draw an upward reaction right here, and we'll call it BY, okay? Now that is technically an assumption. It's a correct assumption. I think we can all probably guess that, but it is an assumption. If we do the math for this problem and we get a positive answer for BY, that means that our assumption was correct. If we get a negative answer, that means that we just assumed the incorrect direction and it is in fact acting downward. Or we have a math error and whatnot. That's also always possible. Okay. So we have BY. We also have two reactions here, AY and then an AX. So which way do you want me to assume AY is acting? Up as well. Okay. There might be a few problems this semester where we purposefully make an incorrect assumption so that you see what happens with the math. And I do that because there are problems in this class where it might actually be difficult to figure out which way a reaction is acting up or down because the structure is kind of complicated. But again, the idea is to get you comfortable with the fact that it doesn't really matter which way you assume. All right, and for the horizontal reaction, I'm going to assume that it acts to the right. I think that for the most of you can probably guess that it doesn't really matter which way I assume AX acts. But we'll get to that here in a little bit. So far, so good? Now, okay, so we have three equations, three unknowns. Now, three equations, three unknowns begets the idea of a 3x3 system of equations. Remember, like matrix math, where you have the 2x plus 3y plus z equals 4, and then the other equation, and then we have to put it in our 3x3 equation solver. I really don't want to do that if I can avoid it. And a lot of times we can avoid it by being choosy both with respect to which order we look at these equations and more specifically where we sum moments, okay? Remember, a moment is defined as a force multiplied by a moment arm, a perpendicular distance from the point in question to the line of action of the force. Everybody remember that? So when we're solving for unknowns, a lot of times it is advantageous to sum moments about a point in which a lot of our unknowns are intersecting so that we don't have to deal with a lot of them. So like, for example, if I were to sum forces in the y direction first, I would have an unknown here, I would have an unknown here. So I would have an equation that would have two unknowns. It really wouldn't give me an answer would just give me an equation that I'd have to substitute back into later. And I don't really want to do that. I kind of just want to directly analyze the problem. So I propose we need to sum moments first. But let's be a little choosy. Let's be crafty. If I'm going to sum moments, about which point do you think I should sum moments? A. We can sum moments about A. That will eliminate two of our unknowns because AX and AY generate no moment, and we would just be isolating our unknown at B. Does that make sense? Now, if we want to get hyper-specific, we could also sum moments at B, because not only does this unknown pass through point B, but the line of action of AX passes through point B as well. Does that make sense? And I mention that because we are going to be dealing with like frames that have incline rollers, and so these are some strategies that you might want to consider. So far, so good? All right. So we're going to sum moments about point A. So this is going to be the first equation that we use. Sum moments about point A. Now I do this a little differently than you might have done in statics. Probably what you did in statics is you wrote out a big old equation, right? That's probably what you did in there. That's not what I do. What I do is, I'm an engineer. I like to do things with tables. So what I'm going to do is I'm going to draw myself a little table, and I'm going to put all the moments that are spinning this way and all the moments that are spinning this way. And I'm just going to list them out in the table. Now, to be clear, you do not have to do it this way. If you don't want to do that, that's fine. I'm not one of those ones to say the only right way of doing a problem is the way that I do it. That's fine. I'm not worried about that. But this is just how I do it. So what I'm going to do is I'm going to sum moments at A, and I'm going to just start listing my moment contributions. So the reason I kind of like to do it this way is I can just sort of start at the left and just start checking off forces and components throughout the entirety of the problem. So if I'm summing moments here, let's just make sure we're all clear. Do I have to consider AX or AY? No. Do I have to consider 20? Okay. So we agree that 20 kips generates a moment at A. Let's make sure everybody's following. Do you think it belongs on this side of the table or this side of the table? The left or the right? Left, because if I'm at A, it's spinning like that, right? And from A, what is the moment arm? 6 feet. All right, so what I'm going to do is I'm going to say that this is, I'm going to put 20 kips and 6 feet. And so this is 20 kips. I sometimes just use a little K for kip, for KIP. We tend to write the term kip quite a bit, so that's just my shorthand. So 20 times 6, and I'm putting it on this side of the table because it's generating moment that way. What about the 30 kips? Does that generate moment? Yes. Left or right? Left. All right. What is the moment arm from A? 15 feet, not 9 feet, 15 feet, because it is from A. Our eye is fixed upon point A when we're doing this. So, there we go. Okay, what about the 18? Does that generate moment? From A, how far? 22. Okay, so okay. All right. Is there anything that generates moment the other way? By, right? At a moment arm of? 30 feet. Okay, so okay. So basically, when I say that the sum of moments equals 0, another way of thinking about that is that the sum of all the moments going this way have to equal the sum of all the moments going this way. Okay? So I just like to write it in a table. It's a little easier to sort of see and organize for my brain, for me. Okay. So what I like to do is I like to say, okay, all right, so let's see, 20 times 6, that's 120. 30 times 15, what is that? 450. 18 times 22, I'm not that good. I got to look that one up on my cheat sheet. That's 396. So 120 plus 450 plus 396, what is that? 966. Okay, so 966. What are the units for that, by the way? That's a moment, so it's kip feet or foot kip, either one, doesn't really matter. equals by times 30. So there's my equation, right? The sum of moments equals 0 basically means that this must equal that. And if I'm solving for by, I just divide both sides by 30. And then, therefore, I'm going to use this symbol quite a bit. If you ever see me draw these 3 dots, that means therefore. So therefore, by equals what?
32.2.
32.2. Do I have a second on that? Yes? Okay. Now, the way I'm going to do this is I'm going to write that by equals positive 32.2. And some of you are like, well, yeah, it's positive, but I'm doing that formally to indicate that I assumed, so I got a positive value, okay? I assumed that this was upward. So the fact that this is positive, what that really means is that by is 32.2 kips upwards. See, remember, this is a force, right? Remember from engineering mechanics that forces are vectors? What are the two facets or aspects of a vector? A vector must contain 2 things. Say it again. Direction and magnitude. So, to be honest, I really don't care that it's positive or negative, because positive or negative is a function of whatever assumption that you made. The truth is that the magnitude is 32.2 and the direction is up. Does that make sense? That is the answer, okay? Because that is the only way of describing that is independent of whatever your initial assumption was. Make sense? All right, so far so good? Okay, all right, so we have one of our reactions solved for. We know that by is 32.2 kips going up, okay? Now, if we want to think of this as sort of like a checklist, we've used this equation, okay? Now, there's technically nothing stopping us from just using it again, but I kind of like to cycle through each of these equations one by one. So now that I have summed moments and have solved for this term, why don't I now sum forces in the y direction or the vertical direction in order to solve for this one? Because if I had done that first, I would have gotten an equation with 2 unknowns, but that isn't the case anymore. Because yes, I have AY and BY that are both vertical forces, but I now know what this is. Does that make sense? Everybody with me on that? Let's just go through it and make sure we're all comfortable, okay? So we're going to now sum forces in the y direction, and like before, what I'm going to do is draw myself a little table and put everything up and everything down. In other words, everything going up on the left, everything going down on the right. Do I need to consider AY? Yeah, right? It needs to go over here, right? Do I need to consider AX? No. Again, just go through the entire system. What about the 20, the 30, and the 18? Do I consider those? You bet. And they all go over here. Do I need to multiply them by a distance? No, because I am summing forces. I am not summing moments. Okay? And what am I forgetting? I've got AY, the forces. What am I forgetting? BY. But I know what BY is. So what I'm going to do is I'm going to write BY is positive 32.2 kips. And everybody can read the handwritings come through clear? So what I'll say then is AY plus 32.2 kips. Again, this is all a summation, so we're just summing everything. All right, so 20 plus 30 is 50. 50 plus 18 is 68. All right, so this is 68 kips. So therefore, AY is what? 35.8, and a positive 35.8 at that, right? So positive And again, the positive doesn't really matter. What matters is we assumed upward, and our positive value means that assumption is correct. The answer is 35.8 going upward, right? All right. So, everybody with me so far? So we've used now this one. So now what? Am I done? I got to sum forces in the x direction, but what's that going to yield? Ax equals 0. Okay. For this problem, I would probably just do something like this. I would probably not draw out a table and put a left arrow and a right arrow. I would probably not do that, and I'm not going to make you all do that. But I do want you to make sure that you are developing the mental discipline to go through all of them, because we are going to have problems with loads going this way and loads going this way and loads going like that, and it is very easy to just go, oh, it's 0, because that's what we were doing on the first couple of problems in Dr. Mike's class, in class examples. Well, that might not be the case on a homework or an exam problem, or in even some of the problems we do in here. So I just want to make sure that you're developing that discipline to go through all of them. Does that make sense? So here's my calculations. If I want to summarize the problem, so I have AX equals 0, AY equals 35.8 kips upwards, BY is 32.2 kips upwards. And that is our answer. And I would appreciate it if you would do that on the homework assignment, like just, here's all these calculations, but there's the answer. Makes it a lot easier to grade if I just know what the answer is, okay? So let's take a step back. It's been a while probably since you've done a problem like this, so let's just make sure we're all comfortable with this. Any questions? Everybody good? Not too bad, right? So like I said, we start off with a basic problem. Then we're going to take that problem, we're going to ratchet it up just a little bit, okay? So where are we going to ratchet this problem up today? Well, we're going to ratchet this problem up by taking our types of structures, and we're going to start looking at different types of loads, okay? So I want to talk now about concentrated loads versus distributed loads, okay? What we just did in this past problem, what we did here, these are concentrated forces. This is a 20,000 pound load that is just right there at a single point. Do we deal with that type of effect in the real world? Yes, we do. Like a common place where we would see that is if we have beams connecting into girders, and those girders have to support the end weight of those beams all at that point of connection. So yes, we do experience, utilize concentrated loads. If you ever hear me use the term point load, that's what I'm talking about as a concentrated force. Loads can also be modeled as distributed loads. So instead of lumping 20,000 pounds as a single load on a beam, we spread it out over a given area. A lot of times when we're initially specifying loads on structures, we tend to specify them as distributed loads or pressure loads instead of point loads. So like to give you an example, here's an image that I took online of a ballroom that you might find in a hotel facility or what have you. And the ballroom is packed full of people, okay? No structural engineer is going to say, well, each person weighs, I don't know, 180, 190 pounds, so let's analyze these beams for about 500 point loads of 180 pounds apiece. That's kind of silly, right? Instead, what we might do is we might say, okay, this is a ballroom, and at its worst case scenario, we might design that floor for a pressure load of something like, I don't know, 100 pounds per square foot. And then what we would do is we would take that pressure load and we would distribute it to beams or various elements on the structure. And so when we look, let's say, at one of these beams might be considered simply supported with a distributed load on top, right? And so as structural engineers, we have access to various codes and specifications that will allow us to ensure that when we're designing structures, we're all using the same type of load set. One of the most common examples of this is ASCE 7. You might hear this in a concrete design class or a steel design class. For example, if I'm designing a classroom, I might have a different load set than if I'm designing, I don't know, a library. I think I might have mentioned this earlier, that if we're designing a classroom, we might design it for about 40 pounds per square foot. So that's about the maximum foreseeable load that we would see on the floor in a room like this. Whereas if we were designing a library, we would design a library floor system for something like 150 pounds per square foot. Why the sudden increase in load? Because libraries have to support all the book stacks that contain all the books that college students don't read, right? So, that was a joke, not very funny. No, but in all seriousness, the loads that we design for are a function of what the structure is being used for, what's going to occupy the system, okay? Does that make sense? Everybody okay with that? All right. Let's talk now. Let's talk about the way those loads can be distributed. Loads can be distributed both in a uniform fashion or a triangular fashion. At least those are the two that we see most used in civil engineering applications. So what we were seeing on the previous slide, maybe something like this. This would be a uniformly distributed load. So it's, in other words, sort of like a rectangle, Whereas a linearly distributed load sort of looks like a triangle. A linearly distributed load might look something like this, like it goes from 0 to a magnitude of 3 kips per foot over a distance of, say, 6 feet. And I'm sure some of you are thinking, come on, Dr. Mike, this is the real world. When do you ever deal with stuff like this in the real world, okay? And by the way, this is not a hyper-theoretical class. This is a civil engineering course, so I'm trying to only incorporate models and representation of stuff that you would see in the real world. So I can give you two very simple real-life examples of where you would see a triangular force distribution. One of them is in fluids land, okay? And how many of you all are in fluids? So you probably haven't talked about this yet, but you will. That if you look at a pressure distribution in fluids, pressure increases proportionally as you get deeper, right? So if we were looking at like a dam that was meant to restrain the forces due to a lake or something, as you get deeper, the pressure on that dam increases. So if we're designing this dam, the dam experiences a triangular force distribution, right? So there is one place where there is a real world example of a triangular force distribution, okay? Anybody already had fluids? I'm just curious, so you know what I'm talking about, right? You've seen this before, okay? Another area that's more directly applicable to just structural engineering is with snow, okay? So has anybody ever been on the roof of a commercial building or a building kind of like this one? Has anybody ever been on a roof of a building like this? Are they like hyper sloped or are they kind of flat? They're usually kind of flat, right? In fact, if you're on there, they're flat. They're sloped a little bit because they have to drain rainwater and whatnot. But usually it's kind of flat. You've got maybe like gravel or a neoprene, rubber sheeting on top. And then there's like a little curtain wall. It's about, I don't know, maybe yay high, something like that. And that's what sort of restrains the activity on the roof, right? So here's what happens. We get a big old snowstorm, right? So there's a big bunch of snow on the roof, and then the snow accumulates, right? I don't know about you, but I've never really been in many snowstorms that didn't have a lot of wind accompanying it, right? So you got a bunch of snow on the roof, and then the wind blows. And what happens is all that snow sort of bunches up along one of those curtain walls, and you get what's called a snowdrift, and you get a nice little triangular distribution of load right there along the wall. And it might not seem like it's that heavy, but if we're talking about packed snow along the entire length of the building, well, that's kind of a lot of force, right? So do we see triangular loads in the real world? Yes, there are two really common examples of it, okay? So far, so good? Now, I seem to remember this Engineering 213 statics class that tells me that if I have a rectangle or a triangle, I can characterize those with both an area and this special point that we call a centroid. Y'all remember that? So, for example, if I have a distributed load that is W high and L long, I can characterize that by collapsing it into a single point load where the magnitude of that load is just the area of this rectangle. And the big question is, where do I put this load? I put it where the centroid is. Because if I collapse this into a single point load right here at the centroid, that point generates, so what we're doing here is the magnitude of this load equals the magnitude of this load. And if we put the point load where the centroid is, I mean, the whole way that you derive centroids is what is the definition of a centroid? It's if you were to collapse this into a single point, it would have the same moment equilibrium. I mean, that's how you calculate the location of the centroid. It's the first moment of area divided by the area. So it's a natural place to consider. Now, for a triangular load, where is the centroid of a triangle? Let's say from this big end. It's not halfway over, it's a third of the way over, right? So we would take the area under this triangle, which would be the base times height over 2, right? Area of a triangle. And we would put it a third of the way over. Does that make sense? And then once we've taken these distributed loads and collapsed them into point loads, we can handle the problem the same ways we did before. Make sense? Let's check that out. Let's check that out in practice. Whoop. So I have another problem I want to go through. So now I have a beam, and now let's take a look at this. So this is what I meant when I said I'm ratcheting the difficulty up a little bit. So now it's not just point loads. I got a triangular load, I got a distributed load, I got a roller in the middle of the beam, you know. But think, like, just from the last problem to this problem, we have ratcheted it. It seems like we've ratcheted it up in difficulty, but you would be surprised how it's not difficult. It's actually pretty straightforward, okay? So let's approach this the same way that we have before, okay? How many unknowns at A? 2, right? So what I'm going to do is I'm going to say, okay, we've got and how many at B? 1. So same thing that we did before. Just because the roller is a little bit in the beam versus at the ends doesn't really matter. It's still a reaction. Okay. Now, we have a point load on the beam. We have a 10 kip load on the beam, but we also have these loads here. Okay, so let's deal with the one that's a little bit easier. Let's deal with this one. I have a 1.5 kip per foot load distributed over a distance of 22 feet. So what that's saying is every foot there's 1.5 kips, and that's for 22 feet. So if I were to collapse that into a single point load, how much total force is that? So it's 1.5 kips per foot for a distance of 22 feet. How much force is on the beam right there for that much?
33 kips.
Say it again?
33 kips.
33 kips. So you just, the area, right? So we'll say 33 kips. So when we're writing our equations of equilibrium, instead of looking at this distributed load, we can just sort of consider this as if it's just another point load, okay? Now, where is that point load? It's placed at a very specific point. We can define what that point is by identifying what is that distance. And what is that distance right there? 11 feet. Okay? I think I can make that a little neater. That is 11 feet. Bless you. So now I have placed a load that has the same magnitude as this and will generate the same moment. Okay? That's what I'm doing here. Okay? What about the triangular load? Okay? here is a load that linearly increases from 0 to 2.4 kips per feet over a distance of 15 feet. If I were to collapse that into a point load, what would that be? How much force is that? I'm curious. Anybody got an answer for me?
18.
Say it again.
18.
18. That's 100% right, because the force is the area of that triangle. 1/2 base height. 18 kips. Is everybody with me on that? It's really easy on these problems to forget the 1/2. Really easy to forget that. So don't forget that. This is a triangle, so the area is divided by 2. That is a common mistake that I've seen students make. Now we also need to locate this. So if we're locating this, how far from here, let's say, is that? What is that distance right there? A third of 15, which is 5 feet. There we go. So this is 5 feet. This right here, if we wanted to indicate that, is 10 feet. Okay, let me make that a little bigger. So does everybody see what I've done here? So now when we start applying our equations of equilibrium, I'm going to sort of ignore the distributed loads and just consider these new idealized point loads. Let's go through that. Let's do it the same way we did it before. Let's some moments at A let's just handle it the same way. Do I need to consider AX or AY? No. Okay. I usually put a little line right there through my reactions just to indicate that's a reaction. Okay, so no contribution from AX or AY. Does this triangular load generate moment? Yes, right? And so what I'm going to consider is 18 kips at a moment arm of what? 5 feet. On the left or right? There we go. Not too bad, right? Okay. Do I consider the 10 kips? Yes, I do. Left or right? Left. And then what is the moment arm from A? 22 and a half, because it's 15 plus 7.5. So 10 kips. There we go. Okay. What about BY? Does that generate moment? Of course it does. At a moment arm of 30 feet in the opposite direction. Okay. And then is there anything else? The uniformly distributed load, a magnitude of 33 kips. Okay. Now let's make sure we get our moment arm right. What is the moment arm going to be? 41, yes, because from AY to BY is 30 feet, so we go 30 feet and then we go another 11. So over here, BY is 30 feet. Let's see if we can be systematic. I like to do it one step at a time. So can somebody tell me what's the sum right here? So that times that, plus that times that, plus that times that? 1668. Do I have a second on that? Second. Okay. Now, just so you are aware, if you see me do that symbol right there, like that's foot kips. It's just a shorthand for it. So again, we're going to be writing a lot of forces, a lot of moments. Anything that we can do to just make it go faster, we're going to do it. So I'll just write foot kips like that. All right, so dividing both sides by 30. I think that's going to be positive. And what is that going to be?
55.6.
Going on. Yeah, so I'll probably just go 2 decimal places and say 55.67, which is 55.67 kips going up. Okay? Do I have a second? Second. Okay. By the way, if we're talking, I'm sure some of you might be asking about significant digits. I'm not saying significant digits doesn't matter, but we're talking about designing beams and columns for hundreds of thousands of pounds, and we're expressing things in kips. Like 2 decimal places, that's fine. That's enough. So that's generally my rule. So. Okay, so let me scooch that up just a little bit so we can see what's going on. So now we're going to sum forces in the y direction, and going up, we're going to have AY and BY, but we know what BY is, so we have AY actually, let me not scooch that. There we go. Come on, I'm going to get this right. There we go. Okay. And then going down, what do I have? I have 18, 10, 33. Bless you. All right, 18 and 10, that's 28, 61. I do get that. Did I get that right? Okay. And then therefore, plus, and so I think it's what, just 5.333? So 5.33, which again, the positive sign doesn't really matter. What matters is the magnitude and the direction. All right. Did I forget anything? Did I forget anything? Don't forget, there's 3 reactions here. We need to sum forces in the x direction to state that AX is 0. Okay, do not forget that. Okay, again, I understand on these problems it just seems like a formality and I'm just being nitpicky. That's fine on these problems. On later problems, that is not going to be the case. On later problems, there's going to be a lot more going on here. So, better to develop those good habits now. Okay. All right. How we doing? See how it got a little bit more challenging, but not really? That's sort of the theme, in my opinion, of this entire class. We're going to do some structural analysis. We're gonna do some really difficult problems, but the whole point is that they're not difficult. They're really, if you just break them down, they're all kind of the same problem, just over and over and over again. So that's really my main theme for this entire semester. Sound good? All right. So here's your homework assignment for this weekend. Right there. Just those 2 problems. I'm going to have you compute the support reactions for this beam and this beam, and I went ahead and gave you the images out of the textbook. You can find this on, it'll turn on Blackboard just like the last ones would. Like I said, I'm going to supply the images for the next, probably this week and next, and then afterwards you'll be on your own with that. One other thing I will mention, this is a course in civil engineering, okay? So for the vast majority of the semester, we will deal in US units, kips, feet, inches, etc., okay? There are a couple of times where we'll throw some SI units in there, but to be honest, the introduction of an SI unit system really doesn't change things that much. This problem would be done the same way if this was kips per feet and these were feet. It wouldn't change the method of the problem in the slides, okay? But until Lowe's starts selling 2x4s in metric, we're using US units because that's what's used, in American construction, okay? Does that sound good? All right, I'm gonna pull up the QR code one more time in case anybody missed it, and otherwise you all have a wonderful weekend.